Okay. All right. So last time we talked about geodesic completeness and the Hopf-Reno theorem, right? So we saw that the manifold being complete as a metric space with the metric induced from the Riemannian metric. This was equivalent to the manifold M being geodesically complete. That means that geodesics could be defined for all time. Okay. And so before we continue, today we'll talk about the curvature of a manifold, sectional curvatures, and the curvature operator. So before doing that, I thought it might be good to say a few things about parallel transport. So let's recall that if gamma is a smooth curve, then we can look at the space of parallel vector fields V along gamma, whose covariant derivative is identically 0, right? So as we've seen that this is isomorphic to the tangent space at any point along the curve, right? The isomorphism is just the evaluation map. V goes to V of T naught. Okay, so this is a finite dimensional vector space of dimension n. And gamma is a geodesic if and only if gamma prime is a parallel vector field along gamma. And in 2 dimensions, we can say what parallel transport looks like. So suppose the dimension of M is 2. And suppose gamma is a geodesic. Then along a geodesic in 2 dimensions, parallel transport is not so hard to describe. So here's gamma, a geodesic. Then first of all, if I choose a normal vector to the curve at a point, say at gamma 0, I choose a normal vector n, right? So a unit normal vector. So suppose n is perpendicular to gamma prime 0 and norm n is 1. Then if I let capital N be the unique parallel vector field along gamma such that n of 0 is equal to this normal vector little n, right? Then first of all, note that if I look at the length of n, then this is constant because ddt of norm n squared, this is ddt of inner product n, which is by the metric compatibility to capital D dt n inner product n. And since n is parallel, this dn dt is 0. So this becomes 0. So this means that norm n is constant, and so it's constant equal to 1. So n is a unit vector field along gamma. And furthermore, similarly, the vector field n is in fact always perpendicular to the curve, because the ddt of the inner product n with gamma prime, this is dn dt inner product gamma prime plus n d gamma prime dt, and dn dt is 0, d gamma prime dt is 0 since gamma is geodesic. So this is 0, right? So that means at all points along the curve, this vector field n is a unit normal to the curve, right? Yes? Okay.
Yes.
So that means the parallel transport of this unit vector is just given by taking at each point the unit normal. Of course, there are two unit normals. There's another one in this direction. But if I start from one, then there is a unique continuous choice of unit normal vector field along the curve, right?
Right.
Okay, once I
Yes.
choose an initial unit normal, then by
Yes.
continuity, it has to stay on the same side of gamma in a sense, right?
Right.
Okay, so I can forget about the other unit normal. So this will be my vector field n. So parallel transport of a normal vector is just given by in 2 dimensions. Since in 2 dimensions, there's a unique normal direction. So it's just given by taking the normal vector at each point. Okay. So if I take the normal vector at each point, that will give me a parallel vector field. Is this clear? So this is just parallel transport. This is only for a geodesic though, right? We use the fact that gamma is a geodesic here. Okay, so for a geodesic to parallel transport, the normal vector, you just take the normal vector along all points. Okay.
Right.
Right. And what about a vector which is not normal? Well, for that, the same argument will hold, right? If I take an n, if I take any for any vector v which is right, we have t of norm v squared will be 0, and also by the same calculation as here, the inner product of v with gamma prime will be 0, and also the inner product of v with the normal vector, right? Okay, by the same calculation as above, right? So what is this? This means that v has the same length, and with respect to this this gamma prime and n, these form an orthonormal basis at each point along the curve, right? So these inner products are just the coefficients of v with respect to this orthonormal basis. So these coefficients are the same. And geometrically, what does this mean? This inner product v with gamma prime, this is the length of v into the cos theta, right? And length of v is constant.
Angle.
So that means cos theta is constant. So that means the angle that a parallel vector field v makes with gamma is constant. Okay, so this is how you parallel transport in 2 dimensions along a geodesic. You start with some angle, and then you just take the same angle along the curve. That will give you the parallel transport. Is this clear?
Yes.
Any questions? Okay, you take the same length and the same angle. Is this clear?
Yes.
Yeah. Okay. So, I mean, basically, so V is parallel along gamma if and only if length V, norm V is constant, and inner product V gamma prime is constant. Okay, so one direction is clear. If V is parallel, then of course norm V is constant and inner product V with gamma prime is constant. For the other direction, note that norm V squared is inner product V gamma prime squared plus inner product V n squared, right?
Right.
So if norm V is constant and inner product V gamma prime is constant, then inner product Vn squared is constant, right?
Right.
And this is continuous. So, well, if it is zero, then that means that V is just a constant multiple of gamma prime, and so V is parallel. Otherwise, if this V inner product n is non-zero, then it has to, if the square is constant, then the function itself is constant, right?
Right.
It can't take both positive and negative values, right?
Right.
Then it would have to be zero somewhere. Okay, fine. So, so this implies that Vn is also constant, right?
Yes.
And then this means that, so V is equal to alpha gamma prime plus beta n,
Right.
where alpha beta are real numbers,
Constant.
they're constants, and alpha gamma and n are parallel, and so this is the space of vector fields is parallel. So I mean the space of parallel is a vector space. So this is also a parallel vector field. Okay.
Yes.
Okay, so all you need is that the length and the angle geometrically for a vector field to be parallel along a geodesic in 2 dimensions. It just means that its length is constant and its angle with the curve is constant. All right, that is parallel transport in 2 dimensions. You just keep
Right.
the angle constant. All right. That's clear?
Yes.
Yes.
So I should have said this earlier, but anyway, you just keep the angle constant and the length constant. Okay. Infinitesimal, it's like you have a parallel tube here, right? These vectors sweep out a parallel tube. Oh, all right. So this is parallel transport in 2 dimensions along a geodesic. Okay. So now I'll come back to this. Let me come to a rather abstract definition, but we'll make more sense of it as we go along. So we're going to talk about the curvature of a Riemannian manifold. So let nabla be the Levi-Civita connection. Okay. So then, first of all, we define the curvature operator of M as a R trilinear map from vector fields, cross vector fields, cross vector fields, 2 vector fields. What is the map? So I take 3 vector fields, X, Y, Z, and then I form a 4th vector field, R of X, Y, Z, defined to be nabla Y of nabla X of Z minus nabla X of nabla Y of Z plus nabla bracket XY of Z. Okay. So this might seem very algebraic, but it's a measure of how much the covariant derivatives with respect to x and y fail to commute, right? Okay. So if x and y are vector fields which commute, then this bracket xy is 0. So this last term vanishes. And then it's just a commutator of these covariant derivatives, right? It's nabla y, nabla x minus nabla x, nabla y applied to z. Okay. All right. Now, the point of this nabla bracket xyz term here is that actually with this term, what happens is this map R, this becomes C infinity M trilinear. Okay. So that means if I multiply any of x, y, or z by a function, then that function f will come out. Okay. This will become f times R of x, y, z. Is this clear? Yeah, I mean, so this is it's a computation you have to do using the Leibniz for the Levi-Civita connection, right? Using the Leibniz rule for the connection, you can check that this is C infinity M trilinear. Okay.
Yes.
And therefore, as we said earlier, once you have a map which is C infinity M trilinear, then this localizes to a point, right? So this R of x, y, z at a point P, this will in fact only depend on the values of x, y, z at P. Okay. So
right.
Why is that? So it's just the same argument that we've seen earlier. So first of all, note that R is a local operator. That means R of x, y, z restricted to an open set U. This only depends on x, y, and z restricted to U. Right? This is clear because the connection, these covariant derivatives only depend on the germ of z, right? Here. And the germ of x and y at a point. Is that clear? Yeah?
Right.
Okay. So this is a local operator because the connection is local. And now once you know it's local, then I can look at this in a chart, right? So I can look at R restricted to some chart U. All right. And then in the chart, I let my X, Y, Z be linear combinations of the basis vector fields del del xi with coefficients which are functions ai, bj, ck. Okay. And then since R is C infinity U trilinear, right? This R of x, y, z, p, by trilinearity, these functions ai, bj, ck, these functions will come out, right?
Right.
And so become just a sum over ijk, ai of p, bj of p, ck of p into R of del del xi, del del xj applied to del del xk at p. Okay. And so this only depends on the values of ai at p, bj at p, ck at p, right? And these only depend on the values of x at p, y at p, and z at p. Is this clear?
Yes.
Yes, sir.
So therefore, this curvature operator actually is a tensor. So I can localize it to a point, and so then we get what's called the curvature tensor of M. So this is an endomorphism valued 2 form. Okay, let me explain what this means. So this is defined as follows. So for P, a point in M, R sub P, this is going to be a bilinear map from TPM cross TPM to the space of endomorphisms of TPM. Okay. So how is this defined? I take a vector V and a vector W. Then I get an endomorphism of TPM, R sub P of VW, this goes from TPM to TPM. What is this linear map from TPM to TPM? Is the linear map U goes to R of XYZ at P, where XYZ are any vector fields such that X at P is V, Y at P is W, and Z at P is U. Is this clear? So this is, you can think of as R of VW applied to U. Okay. So as we've just, this is independent of the choices of X, Y, Z, right? This just depends on the values of X, Y, Z at P, and those are fixed equal to V, W, and U. Okay. So for each pair of vectors V and W, I'm getting a linear map from TPM to TPM, right? So what I have, and since this R is trilinear, that means this map will be bilinear in VW, right? So this is a bilinear map from TPM cross TPM to endomorphism of TPM. All right. Is this clear? And notice that this map is alternating. That means if I interchange VW, then R of WV is equal to minus R of VW, right? That follows from the definition here. If I interchange XY, then this changes sign, right?
Yes.
Okay, if I interchange XY, this changes sign. So therefore, this is an alternating bilinear map. Okay, this is an alternating bilinear map from TPM cross TPM to endomorphisms of TPM. All right. So it's like a two form, except that instead of taking values in scalars, it takes values in endomorphisms. Is this clear?
Yes.
Yes.
Okay, so I mean, this is a general concept. I mean, if I have E over M, which is a vector bundle, okay, then what is an E-valued K form? This is a section of the bundle wedge K M. So if it was just wedge K T star M, it would be a K form. But if it's valued in E, then all I do is I take the tensor product with E. Does this make sense? Then this is valued in E. It's a E-valued K form. All right. So for example, if you take E to be the endomorphism bundle of the tangent bundle, yeah. So that means, I mean, the fiber over a point P, EP, is just the vector space of endomorphisms of TPM. Okay. All right. So this is a vector bundle of rank n squared. Yes. Okay. So then the curvature operator R, this is RP belongs to what? This belongs to wedge K, sorry, wedge 2. TP star M tensor EP. Does this make sense?
Yes.
Yes, Orkojit, is this okay?
Yes.
Right. Tensoring means that, you know, for each pair of vectors here, basically now, you know, VW goes to So RP is what? It's a map. VW goes to R of VW, right?
Okay.
So this is an element of this EP, which is the endomorphisms of TPM.
Oh.
Right.
Oh.
So it's like you're taking
So,
a scalar value two form, and then you're tensoring it with
oh,
an endomorphism, right? So makes sense, yeah. Okay.
okay. So this tensor is equal to home of these two things, like that.
Well, it's not
That's why you
exactly
are.
Hom because it's alternating. So it's a subspace of the Hom. It's a subspace of, but it's not Hom even, it's multilinear maps. So yeah. Is this all right?
Yeah.
You know what the tensor product is, right?
Right. Okay.
Yes. So,
Mhm.
okay.
Mhm.
So this is what the curvature operator, you can think of it this way. All right. Anyway, either way, it's just a alternating bilinear map from TPM cross TPM to endomorphisms of TPM. Okay. All right.
Okay.
Okay. Now, I want to see geometrically what is this R of VW. Okay. What is this endomorphism? Geometrically, what is this? Right. So, how do we describe this geometrically? So the description, we did this last semester, but let me remind you the following proposition. I'm not going to prove it. We did the proof last time, last semester. So the proposition says the following. So given VW in TPM, okay, you let XY be vector fields in a neighborhood of P, which commute. Okay, so bracket XY is 0 and such that X at P is V and Y at P is W. Okay, so note we can always find such vector fields. Yes, do you see how to find such vector fields?
Yes.
How would you find such vector fields?
So I take I mean, I can write W in terms of a linear combination of W and V at that point, evaluated at the point P. I can take it just linear combination of coordinate vector fields, right? So on the
Del
neighborhood, I
xi.
just del
Yeah.
xi. Yeah.
Hmm.
So on the neighborhood, I can define it like that, and then I multiply with just a bump function on that neighborhood. Then I will get a vector.
Yeah, so X and Y are basically linear combinations of del xi's with constant coefficient. The point is the
Yes.
coefficients are constant. Therefore, the
Constant.
bracket of xy is 0, right? Because the coefficients are constant. Right? The point is the coefficients are constant.
Right.
That is the
Yes.
point, right? Therefore,
That
the
is
bracket is 0. Because the bracket of del xi, del xj is 0 for all ij. So if I take linear combinations with constants, then the bracket will stay 0. Okay?
Yes.
And if I choose the linear combinations appropriately, then I can get whatever vectors I want at P, right? Okay, that's it. Okay, so such vector fields exist, fine. So now suppose I take two such vector fields whose values at P are V and W and which commute, okay? Then for T small, let's look at a small parallelogram. So because the flows commute, if I flow along X for time T, then Y for time T, then minus X for time T and minus Y for time T, I will come back to the point P, right?
Yes.
Okay. So now I have a loop based at P, which is piecewise C1. And therefore, parallel transport makes sense along piecewise C1 curves also. Okay. So I can do the parallel transport along this small loop, right? So let me call that P sub T. Okay. So since this is given by parallel transport, remember parallel transport with respect to the Levi-Civita connection, it acts by isometries, right?
Right.
Yes. So this P sub T this will be an isometry from TPM to TPM, okay, which is parallel transport along this small loop. Okay, now you let the length tend to 0, so let T tend to 0. Then PT, of course, will converge to the identity, right? Since you're parallel transporting along small loops. But, and you would expect that since these sides are of length of order T, the parallel transport will be of order T distance from the identity, right? But actually what happens, because you have an X here and a minus X here, the order T terms will cancel and the parallel transport will be actually of identity plus something of order T squared. Okay. All right, that's because this X and this minus X and the Y and the minus Y, the first order terms will cancel. All right. So we did this calculation last semester. Have a look. Have a look in the notes. Okay. So the first order terms will cancel. What remains are second order terms. Okay. And so therefore, to get a limit, what you do is you look at the limit PT minus the identity divided by T squared. Okay. This limit exists and this equals R of VW. Okay. Okay.
Okay.
So this is the limit. It's a derivative, if you like. If I replace T squared by some variable S, and this PT I call instead of, this will be P of square root S, I call that some Q of S. So then this is a derivative along a curve of isometries passing through the identity, right? Yes?
Right, yes.
So what kind of endomorphism will you get when you differentiate a curve of isometries passing through the identity? What will you get? Utsav?
Yes,
This is a basic Lie group question.
yeah, okay, get it. It's right. So it's skew symmetric.
You'll get a skew symmetric matrix, right? You'll get a skew symmetric linear map. Okay. So as a corollary of this, we obtain that R of VW, in fact, is skew symmetric for all VW. So let's just see that. So skew symmetry means this identity, right? Inner product R VW with X comma Y is the same as minus inner product X with R VW Y. Okay. So why is that? So these parallel transport isometries, these PTs are isometries. So that means PT star PT is equal to identity for all T small. And because PT minus identity over T squared, this converges to R of VW. That means that PT has this second order expansion is equal to identity plus T squared R VW plus little o of T squared, right? Okay. So now I look at this PT star PT minus identity. This is 0, right? So I have 0 equal to PT star PT minus identity. Now I divide this by T squared and take the limit as T tends to 0. So this PT star PT, I use this expression for PT. And so PT star will be identity plus T squared RV star plus little o of T squared. So when I multiply PT star and PT, what will happen? I'll get identity plus T squared into RVW star plus RVW plus there'll be higher order terms, right? Which are little o of T squared. Those I can forget about. So when I subtract identity, this identity and this identity here will cancel. And this T squared and this T squared will cancel. And the little o of T squared terms divided by T squared will go to 0. So this limit will be nothing but RVW star plus RVW. Is this okay?
Yes.
All right. So that tells me that the curvature operator, it takes values in skew symmetric endomorphisms. Yeah, so actually the curvature operator RP, this actually goes from TPM cross TPM to the Lie algebra of the special orthogonal group of the tangent space. So little so of TPM. Does this make sense?
Yes.
Okay, that's because basically PT, that's the parallel transport. This belongs to SO of TPM for all T small, right? Okay, is this clear? Yeah. Okay, why the S here? Why is determinant 1? Because it's close to, PT is close to the identity, right? So therefore it's determinant, if it's orthogonal and close to the identity, it must have determinant +1, right? Yes?
Yes.
The determinant is either +1 or -1, right? If since it's orthogonal.
It's
Yes.
close to identity, so it's an identity component, so it should be so.
Yeah. If it's close to identity, so then it must be +1. The determinant has to be +1. So therefore, when you differentiate this curve in SO-TPM passing through the identity, you'll get something in SO, little SO-TPM. All right?
Yes.
Okay, does this make sense?
Right.
Right? Okay. Now, maybe it's a good time before defining sectional curvature. Yeah, let's look at a special case where n is equal to 2. Okay. All right. Yes. Okay. So say V is equal to TPM. This is isomorphic to R2. Right. And so what is SOV? This is isomorphic to S1, right?
Yes.
In 2 dimensions. And so little SOV, the Lie algebra, this is isomorphic to R, right?
Yes.
Okay. And this S1, okay. So, okay, so we're in 2 dimensions. So V is a 2-dimensional vector space TPM, a 2-dimensional inner product space. So SOV is isomorphic to S1, and this is generated by rotations, right? So it's a 1-parameter subgroup, e to the t j, right? And this Lie algebra is generated, it's just generated by one element j, right? Where j is the unique skew-symmetric matrix, which, I mean, is a basis for the skew-symmetric matrices, right? This matrix. So this is nothing but your multiplication by I, right? This is rotation by 90 degrees.
Yes.
Okay, this is the generator of the Lie algebra here. Yes, okay. So if I take an orthogonal basis, then E1 goes to E2 and E2 goes to minus E1, okay? Right?
Yes.
Okay, so J, this is rotation by 90 degrees. And this is J. All right, fine. Yeah. Now, let's look at our curvature operator now. So R, so first of all, notice that we have an isomorphism. We have an isomorphism from SOV, little SOV to R. how do I get this? So, so phi from little SOV to R. So little SOV is basically what? It's they're just elements of the form Tj, right? So the isomorphism is going to send Tj to T, right? Yeah, so how do I get this T? This I can write as, so if I take a skew symmetric linear map capital T, then what will this coefficient little t of J be? Little t will be the inner product of capital T E1 with E2. Yes?
Yes.
Because this will be TE1 is little t J E1, inner product E2, right? So this is inner product TJ E1, E2, and JE1 is E2. So this is T inner product E2, E2, which is T, right? Okay.
Yes.
So I have this isomorphism SOV to R here. Okay. So now I can look at my curvature operator R sub P. So this is a bilinear form taking values in SOV, right? But SOV is isomorphic to R, right? I have this isomorphism phi. So I can think of this as taking values in R, right? All right. Makes sense? Yes?
Yes.
Okay, so this VW, this goes to, what is this? So what is this bilinear form? This goes to T equal to R of VW. This is in little SOV, okay? And then this maps to, under phi, this goes to inner product T E1, E2, right?
Yes.
So what is T? T is R of VW. So this whole thing becomes inner product R VW E1, E2. Okay. So now this, so let me call this composition, let me call this Q. So Q is equal to phi composed with RP. Okay. So, okay, maybe let me just put this as Q here. So here I'll put RP and here I have phi. Okay. So this goes from TPM cross TPM to R, right? Okay, this is an alternating two form on TPM, which is two-dimensional, right? So what do we know about an alternating two form on a two-dimensional vector space? What do we know about it? Okay, what do we know about an alternating n form on an n-dimensional vector space?
You know the determinant?
Yeah, it's a multiple of the determinant, exactly. It's a multiple of the determinant. So that means Q is equal to lambda times det, yes?
Yes.
Yes. And how do we get lambda? How will we get this lambda? How do we get lambda?
Determine,
What can we do to both sides of this? Can we apply this to something nice so that we are left with lambda on one side? How do we get the lambda? Come on, it's an easy thing. Come on, come on.
apply to one to one. Yeah.
Exactly. Just apply it to E1, E2, right? So Q of E1, E2. Exactly. Q of E1, E2. This will be lambda det of E1, E2. And det of E1, E2 is 1, right? So this is just lambda. Okay. So here I should have said in the beginning that E1, E2 is an orthonormal basis of TPM. Okay. So where is this? Yeah. So okay. E1, E2. This is an orthonormal basis. Okay. All right. Yeah. So lambda is therefore Q of E1, E2. So that means lambda is, what is this Q of E1, E2? Look at the definition of Q. It's going to be inner product R of E1, E2 applied to E1, inner product E2. Okay. All right. Yes.
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 Now this thing here, this is what is defined to be the Gaussian curvature of, so M is a surface, right? This is defined to be the Gaussian curvature of M at P. Okay. So this tells you that this alternating bilinear form, what multiple of the determinant it is, right? What multiple of the determinant it is. Okay. Yeah. So in other words, you see my, if I call this to be K sub P, okay, then this Q, this is a two form. This Q is equal to K into d vol, right? Into the volume element of the Riemannian manifold. Does this make sense? Where K is a function from M to R. This is the Gaussian curvature. Does this make sense? Yes?
Yes.
Because Q is lambda times the determinant. The determinant here is it gives the volume form, right? It's one on every positively oriented orthonormal basis, right? So, okay. Yeah. So now, let's look at some examples, right? So you've heard that the sphere S2 is positively curved and the hyperbolic plane H2 is negatively curved, right? How can we see this geometrically, right? So let's look at some examples. So one, let's try and look at the curvature of S2, okay? So that will be computing this quantity, inner product R E1, E2, E1, E2, right? Okay, so let's look at an example, M equal to S2, okay? Yes? So I have to take a point P and I take E1 and E2, right? An orthonormal basis at P, yes? Okay, on the sphere. Now, I want to look at vector fields which are tangent to E1, E2 at P and which commute, right, on the sphere. So what I can do is E1, I can extend this to a geodesic, which is a great circle. So for example, the equator, say, all right. And E2 I can also extend to a geodesic which will be perpendicular. It will be, so if E1 is tangent to the equator, this will be tangent to a longitude like this. Okay. So so what I'm going to do is the following. Let me draw this picture nicely. Right. So I'm going to take a very small quadrilateral like this, okay, where the sides, the horizontal sides are parallel to latitudes, okay. So one vector field x, the flow of x is along latitudes, all right. So the equator is one integral curve of x, okay. This is North Pole, South Pole. And the other vector field is flows along longitudes, okay.
Yes.
So these are my vector fields, x and y, all right. So x is acting like this along latitudes. And y is acting like this along longitudes. So clearly these two commute, right? Yes?
Yes.
Okay. Now what am I supposed to compute? I'm supposed to compute parallel transport along a small quadrilateral like this, right? So I go along x, then y, then minus x, and then minus y like this, right? Or I could go the other way, say around y, x, this way, this way. Yeah. So maybe let me change my E1, E2. So, so it's just a matter of notation. Let me do it this way. Yeah. So let me make this one. Let me make E1 the vertical vector and E2 the horizontal vector. That will be a bit easier. Okay. And so let me make this vector field, the vertical one x, and the horizontal one y. All right. I'm just changing notation. Okay. Is this all right? Yeah.
Yes.
Okay. And now I'm going to yeah, so I'll just change the direction of this. Sorry. Okay. So I'm going to go like this. Okay. So what am I supposed to do? I'm supposed to look at R first, E1, E2, E1, right? Okay, so this is a limit. T tends to 0. PT E1 minus E1 over T squared, right? Yes?
Yes.
Okay, so I have to parallel transport E1, this vertical vector, along this quadrilateral. So what happens? All right, so let me start here. So this longitude is a geodesic and E1 is tangent to it. So the parallel transport of E1 along E1 will just be the tangent vector to this geodesic here, right? Of E1 along this vertical segment, I'll just get the vertical tangent vector here, right? Yes? This is a geodesic, right? So the parallel transport of the tangent vector is just the tangent vector.
Yes.
Right? I just transferred E1 to E1 over here, right? To this vertical vector here. Fine. Now I have to transport along here. Okay, so let me call, say, V equal to the the parallel transport along this curve gamma t. So now, what happens when I parallel transport along this latitude? Now, this latitude is not a great circle, so this is not a geodesic, right? Yeah, this is not a geodesic. So what happens when so then I have to see, so let me call this part, this latitude, say gamma. Okay, so say gamma equal to the latitude. So this is not geodesic.
Normal.
Okay. So I just have to, so now this is perpendicular to gamma. So it's going to, well, gamma is not a geodesic, so it may not stay perpendicular to gamma. Let me look at the inner product of V with gamma prime. All right. I want to see how this, so this gamma is very short. So I just need to look at the change in this. So that's given by the derivative, right? So ddt of V gamma prime is what? This is inner product dV dt gamma prime plus V d gamma prime dt, right?
Yes.
Now dV dt is 0, so this vanishes. So this is just inner product V with d gamma prime dt. Okay. Now I need to compute this covariant derivative. So what is this covariant derivative? Well, this is nothing but inner product.
Tangential component of
Exactly.
W.
So this is ddt of gamma prime, tangential component, right? Okay.
Right.
So now I'm looking at a latitude. What will this look like? So let's draw this latitude here. So this latitude is the intersection of a horizontal plane with the sphere, right?
Right.
So there's some horizontal plane here. This latitude is a circle in this horizontal plane with center at the origin of the horizontal plane. So this d gamma prime dt is what? This is just gamma double prime, right? And gamma is a circle in a plane. So gamma double prime points to the center, right?
Points to the center.
It just points to the center. Your centripetal force or whatever you call it, right? So this this points to the center, okay? This is your gamma double prime. And now what is the tangential component? Well, I have to look at the component in the tangent space. Now the tangent space is sort of a slanted plane like this, right? So if this is horizontal, in this, there will be some component like this. This will be the tangential component, right? Does this make sense? Can you see the picture?
Yes.
So it's going to point upwards, right? It's going to point upwards. So this inner product with V, this is going to be positive. Make sense?
Yes, sir.
Yes.
Okay. So the covariant derivative is pointing upwards of gamma prime, and V is pointing upwards. So this change in V gamma prime, this is going to be positive. So now if V makes an angle 90 degrees here, then that means at the end of it, V will make an angle which is smaller than 90 degrees. You see? Right? The inner product is increasing. That means you move more in the direction of gamma prime, right?
Right.
Yes.
Okay. So this is what the picture. So V will, it will tilt like it was like this at the end of parallel transport. It looked like this. Okay.
Yes.
Now I'm moving along a geodesic. So this again, I move along this longitude. This is a geodesic. So along a geodesic, the angle doesn't change, right? So I come back to something like this. And now when I come back here, I've moved like this, right? This equator is also a geodesic. So when I come here, again, angle doesn't change. So overall, what is the change? I move like this, right?
Yes.
Yeah, so you see, what is the effect of parallel transport along a small loop? It's an infinitesimal rotation, right? It's an infinitesimal rotation. This is rotating infinitesimally in the direction of E2, right?
Right.
So the inner product with E2 will be positive, right?
Okay. Yes.
Make sense?
Yes,
This
yes.
is
Yes.
going in the direction of E2. So this inner product will be positive. That means the curvature is positive. Okay. So, of course, we're not calculating the value of the curvature. We're just saying the sign of the curvature is positive. All right. So if this was E1, then we find that PT E1 looks like this after parallel transport. And so this difference is what you're taking the inner product with E2 with, right?
Yes.
Okay. So this inner product are E1, E2, E1, E2. This is limit T tends to 0. Inner product PT E1 minus E1 E2 over T squared.
Hmm.
So this inner product is positive. So this limit will be positive. Okay.
Hmm.
So for the sphere, K is positive. Okay. Okay, so the sphere has positive Gaussian curvature. And of course, since isometries act on the sphere transitively, and you can see this Gaussian curvature is invariant under isometries, right? Because the curvature tensor will be because the connection is invariant under isometries. So this will be constant, right? So this is some positive constant, okay?
Hmm.
K constant because isom S2 acting on S2 is transitive. Okay,
Hmm.
that's all right, fine. So we get that the sphere has positive constant curvature, all right? So this is what positive curvature looks like. It means basically when you do a small parallel transport, sorry, I'm getting the picture wrong. Aha. So when you do a small parallel transport like this, then if you start with this vector, then you'll transport around, you'll come back to a vector like this, which is, so the change is, has a positive inner product with the other vector, okay? Is this all right? This is the picture.
Hmm.
Okay, so this is positive curvature. Yes, question?
Yeah, so you can say it is greater or equal to 0, right?
I
Why is
know,
it
I know, I know.
positive?
Yes,
Yeah.
yes. Well, look, then you'll have to do some computations. I'm trying to do this
Okay.
without
Yeah,
computations,
yeah.
okay?
Okay.
I'm just trying to give
Fine.
you the qualitative feeling.
Ha.
What is curvature?
Ha.
Then you'll have to do
Okay.
computations, of course. Yeah.
Yes, yes.
If you do computations, you can do computations, they're done in any book, but like you won't understand anything of what's going on.
Yes, yes.
You can compute,
sir,
you can compute using the Christoffel symbols and the derivative
Yes.
of the metric. You can get some formula and you plug in the formula, you'll see it's +1. That will tell you, give you no idea why it is +1, right?
Yes, yes.
So, I mean, that's in a sense, that's useless. So I mean, it's useful also. Okay, fine. It's positive. Yes, it's +1. But I mean, it doesn't tell you how or why
Yes.
it's, what is the meaning of positive curvature, right? So, okay. So, yeah, you're right. This will just tell you greater than or equal to 0. But yeah, you can, if you work hard, you can
Okay, fine.
turn this into a calculation. And, yeah,
Yes.
it'll be positive. Yeah. Okay, now what about a surface of negative curvature? So let's take M to be, say, the hyperboloid of one sheet. So this is like this. Okay. So this is what we sit on, right? Jake mora bole. Yes. This is a hyperboloid of one. Yes. Okay. So this has one central geodesic in the middle. This is a geodesic, all right. And that you can see because the second derivative, right, ddt of gamma prime, this is a circle. So this points inward. And so this is normal to the surface, right? So the tangential component of the acceleration is 0. Yes?
Yes.
Okay, so this is the geodesic here. And these guys you can also see are geodesics, these perpendicular lines like this. Okay, these will be intersections of planes with this hyperboloid. Okay, of vertical planes with this hyperboloid. Yeah, these will also be, yeah. Okay. Now, let's do parallel transport along a small loop like this, right? So, so I'll take a circle at some height here, all right? And I do the same thing here. So what will happen when I do parallel transport of this vertical vector? So when I see 3 of the sides are geodesics, the only side I have to worry about is this. It's like a latitude in the earlier example. This side is not a geodesic, right? Okay, so when I parallel transport along the geodesic, I'll just come here. Fine, the vertical vector will be vertical. Now what happens? So now I have a circle here, right? I have a circle here. So again, if this is gamma, this circle, gamma double prime points into, right? But now notice, if I look at this hyperboloid, the picture, if I take a cross section, it looks like this. My gamma double prime is like this, right? Okay.
Yes.
Right. But what is my tangent plane? My tangent plane is like this, right?
Right.
So now the component in the tangential direction, that will point downwards. Instead of pointing upwards, this gamma double prime tangential component, this will point downwards, right? You see it points downwards.
Yes.
You see from the picture, instead of going upwards like a sphere, in this case it points downwards. This means that this V inner product d gamma prime dt, this will now be negative. And this we saw, this is equal to ddt of V inner product gamma prime, right?
Right.
So now this is negative. So now this will go away from gamma prime. As I parallel transport here, this is gamma prime. This will go away from gamma prime. Now I move along a geodesic, the angle stays the same. And then again along this central geodesic, the angle stays the same. So when I come back here now, I'll see a rotation in the opposite direction, away from E2, you see? So this is my E2 and this is E1. So, I mean, the picture I'll see looks like this now. So this is E1 and this is E2. And now my PT E1 will look like this, right? Sorry, so let me just write this properly. So I'll have E1 here and PT E1 will look like this. Right, so now my parallel transport is going the opposite direction. The rotation is in the opposite direction to the orientation induced by the basis E1, E2, right?
Yes. Yes.
Utsav, is this okay? This picture, yeah?
Yes, sir, yes.
Okay, so this is because along this this latitude here in the hyperboloid, the covariant derivative of the latitude points downwards. So that means the inner product with the parallel vector field V is negative, and so that is the change in the inner product with V. So this is negative. So that means that if V was like here, then over here V will move a bit to the left, right?
Yes.
The inner product was 0 here. Over here, the inner product will become negative. So, right? Utsav, is this okay?
Yes.
Yeah, so the angle will become bigger than pi, right? So when I move back, bigger than pi by 2, sorry. So when I move back here, I'll see a rotation in the opposite direction like this. So this will tell me that my R, E1, E2, E1, this parallel transport, inner product with E2, this will be negative. Okay. So here I'll get a surface where this Kp will be negative. Okay.
Yes.
Yes, sir.
Well, so yeah, so I mean this sort of calculation, these are heuristic. I agree, but they give you the idea of what is the sign of curvature. Okay, so this will give you a surface of negative curvature. Okay. So I don't know if these pictures help or not, but at least they help me to think a bit. So I thought I would share them with you.
I mean, isn't this in sync with the fact that when we look at positive curvature and we look at geodesic features, like which start at the same point and then they might intersect after some time, but when we look at negatively curved spaces, then they'll just spread apart further and further.
Look, that is what you're talking about is a more global property, but this curvature here is an infinitesimal property.
Right, local property.
It's an infinitesimal property, yeah. Right, it's an infinitesimal quantity. So really you should be looking at small pictures, not long-term pictures,
Right.
just short-term,
Yeah.
very small time geodesics, yeah. So, yeah. So, I mean, this curvature is measuring a parallel transport along small loops, basically. That's what it's doing.
Yes.
And in 2 dimensions, you get a scalar, right? One scalar instead of an operator. That measures whether you get an infinitesimal rotation. Now, is that rotation is it the same orientation as that given by the basis or the opposite orientation? Right? That's what it's measuring.
Yes.
Make sense? Yeah. Okay. So I should just say, this hyperboloid of one sheet, I forget if this has constant curvature. Yeah. I think this is, if I'm not mistaken, so wait, it has 2 flaring ends, right? Yeah, this is, I think, biholomorphic to, I mean, it's isometric to an annulus, which is basically this hyperboloid of one sheet. It is, yeah, it's basically the Poincare metric on an annulus. This M is isometric to. So this is an annulus, say, of size 1 and R, an open annulus. Okay. So this open annulus, 1 less than mod Z less than R, together with the Poincare metric on this. Now, what is the Poincare metric? The Poincare metric means, so it means if you take a planar domain, then in most cases, the planar domain will be, the universal covering of this domain will be the unit disk or the upper half plane, same thing, right? And this, in this case, we can see this universal covering as the upper half plane, okay, together with the hyperbolic metric. And this will be the quotient of this upper half plane by a scaling of by some factor lambda. Okay.
Mm.
So this is z goes to lambda z. Okay. So lambda will be positive.
Hmm.
You can express it in terms of R. And this we've done in our complex analysis class, if you remember. I think, yeah, so yeah, so when you quotient, you'll get an annulus, which is bi-infinite at both sides, you see. So these geodesics will become these geodesics.
Longitudinal geodesic.
Yeah, and this central geodesic is this vertical axis.
Then,
This becomes a circle. This becomes a circle. So that's your hyperboloid of one sheet. Okay.
and other geodesics are spiral. Going off.
Yeah. So anyway, this is it, the picture. Okay. This is the hyperboloid of one sheet. Okay. Let me stop and start another class. Okay.
Maybe after 1 minute. Yeah.
Yeah, sure. Let's take a 1 minute break. Sure. 1, 2 minute break. Yeah. Okay, fine. Okay.
Okay.
Yeah. Okay. So anyway, I mean, these I just wanted to give you some feeling for curvature in 2 dimensions. What is Gaussian curvature? Right. So essentially, you're looking at parallel transport along infinitesimal parallelograms. That gives you an infinitesimal rotation, and that the space of infinitesimal rotations is just the real line, right? Little SOV is R, and so this alternating 2 form is a multiple of the determinant in 2 dimensions, and that multiple which you get, that is the Gaussian curvature, right? So so any questions about this?
So are we just saying that the rotation is in positive 90 degree or negative 90 degree? Yes.
I mean, is it, see, it's an infinitesimal rotation, right? So what is the space of infinitesimal rotations? It's little SO of V, right?
Yes.
Right. So what is little SO of V? Little SO of V is isomorphic to R.
Mhm. Right.
So it's scalar multiples of J, right?
Yes. Yes.
Okay.
Right.
This is little SO of V. Okay. Now, that means that my curvature operator, which is going from TPM cross TPM to little SO of V, right?
Mhm.
This I can compose with the isomorphism to R. So then it takes values in R, right?
Right. Right.
So now
Yes.
it becomes an alternating 2 form, right?
Mhm.
Okay. And that alternating 2 form, it is, well, when I say det here, det is really with respect to a basis. So what I mean is this det here is E1 star wedge E2 star. Okay.
Okay.
Yeah. Fine.
Yes.
So where E1, E2 is any orthonormal basis.
Mhm.
And so this now is an alternating bilinear form. So it's a multiple of this E1 star wedge E2 star. And how do I get this multiple? I apply both sides to the pair E1, E2, right?
Yes.
So that gives me lambda. So lambda is Q of this bilinear form, Q of E1, E2. So that becomes inner product R E1, E2, E1, E2. right?
Right.
Now, this geometrically, what does this mean? This is basically this R E1, E2, this is my infinitesimal rotation, right? R of E1, E2. Now, R of E1, E2 is some multiple of J, right?
Right.
It is some T times J. Now,
Yes.
how do I get this coefficient T? I have to apply my infinitesimal rotation to E1 and then inner product with E2, right?
Yes.
Okay, so that's what I'm doing here.
Hmm.
I'm taking R of E1, E2. I'm taking inner product with E1 and then inner product with E2, right?
Yes.
So this gives me so this means that R of E1, E2, this is equal to K times J, right?
Right. Yes. Yes.
Does this make sense? Yeah.
Right.
So exactly, it is giving you the coefficient of the infinitesimal rotation,
Okay.
right? When applied to an orthogonal basis, it's giving you the coefficient. So if K is positive, then it's a positive multiple of J. It's rotating in the same orientation as determined by E1, E2. And if K is negative, then it's rotating in the opposite orientation, right?
Right.
So
Yes.
that's what you see in this picture. The orientation determined by E1, E2, I mean, the positive orientation is going this way from E1 to E2, like this, right? So in this picture,
Right.
this infinitesimal rotation is going in the same, it has the same orientation. It's going in, in the same direction,
Right. Yes.
right?
Yes.
Okay.
Exactly. Yeah.
So here the curvature is positive, and in the hyperboloid picture, it's rotating in the opposite orientation, right?
Right. Yeah.
It's going in the opposite direction. Does this make sense? Yeah.
Yes. Yes.
Yes, sir.
Utsav, is this okay? Yeah.
Yes, sir.
So yeah, so this gives you the coefficient. This if I call this K, then basically, yeah. So R of E1, E2 is equal to K times J, where J is the rotation by 90 degrees, the generator of the Lie algebra of capital SOP. Make sense? Yeah.
Yes, sir.
Okay. All right. So now what do we do for general higher dimensions, right? So general case, n greater than or equal to 2. So we have this abstract information of the curvature operator at each point. This is going from TPM cross TPM to little so of TPM. Yes? Okay. So how do we capture this information in a more geometric way? This is some abstract linear algebraic way of describing curvature. How do we capture it in a more geometric way? So at least in 2 dimensions, we see that we have a nice geometric interpretation, right? We have Gaussian curvature of a surface at any point. So in higher dimensions, what we can do is the following. If I take, what I can do is, I can take 2-dimensional subspaces of the tangent space, okay? So suppose sigma is a subspace of the tangent space, which is a 2-dimensional subspace. Okay, then I can look at a corresponding surface passing through the point P, S sub P, which is the exponential based at P of sigma, well, intersect a small ball around the origin. Okay. So this is a small surface passing through P, right? Yes. Okay.
Yes.
So I'll have some surface here, and which is tangent to sigma. Okay. It's the image under the exponential of a two-plane sigma. Okay, and this will be SP. So if I take some other two-dimensional, some other two-plane, like I don't know which, maybe intersects sigma transversely or something. It's just I can't draw it very well, so I'll get some other surface. So I'll have all these surfaces passing through. So if this is some sigma prime, then this will be, sorry, this will be S sigma, not SP. S sigma. So S sigma prime, this will be S sigma. Make sense? Yeah, I can look at all these surfaces passing through P. Yes?
Yes.
Now for surfaces, I can define their Gaussian curvature, right? And so then I can define something called the sectional curvature in the direction of sigma, this two plane, okay? In sectional curvature in the direction of sigma, K sigma. This is defined to be what? The Gaussian curvature of the surface S sigma at P. Okay. Make sense?
Yes, sir.
Right. So this gives me some information in every two-dimensional direction passing through P, right? I can look at all these curvatures. Now, this is not the original definition of sectional curvature. Well, I'm not sure. Maybe Riemann gave this definition. I'm not sure. One will have to look at Riemann. But actually, this Gaussian curvature of S sigma at P, this can be described in purely in terms of this curvature operator in a purely linear algebraic way. So let me give now that definition. But I wanted to give this definition first because this is geometric. You can see this, right? This is a sort of very geometric definition. Okay, so yeah. So now let's come to what's the standard definition of the sectional curvature? Okay, which is the following. Okay. All right. So note one thing. Because the curvature operator, this endomorphism R of VW is skew symmetric, that implies that R of VW acting on X, inner product with X will be 0, right? By skew symmetry. Yes?
Yes.
Okay, by skew symmetry, this will be 0. Okay. So now we can define the following. So first, for an inner product space V, define for two vectors x, y, and v, define the norm squared of x wedge y to be norm x squared, norm y squared minus inner product xy squared. Okay. So actually what this is, if I look at the second wedge product of V, that means wedge 2 of V, then this is actually the induced norm squared on the wedge product of V with itself, induced by the inner product on V. Okay. So any inner product on V will induce inner products on tensor powers of V and on wedge powers of V, on wedge products of V. All right. So this is actually the norm squared on the wedge product. Is this okay?
Yes.
See, note that what can we say? Look, when is x wedge y 0? if and only if x and y are linearly dependent, right? If I have two vectors, x wedge y is 0 if and only if
Yes.
they're linearly dependent, right?
Yes.
And
Yes.
that you can see from this right hand side, this is equal to 0 if and only if x and y are linearly dependent by Cauchy-Schwarz
Equalities of
right?
constants, yeah.
Right? This is 0 means that by Cauchy-Schwarz, these two are multiples of each other. So they're linearly dependent. Yeah. So this behaves like a norm should, right? This is 0 if and only if x wedge y is 0. So, okay. And it's non-negative and so on. So this is actually the induced norm on the wedge product. Okay. Now we can come to the definition of sectional curvature. So let P be a point in M and let sigma be a two-dimensional subspace of TPM. Okay. So then the sectional curvature of M in the direction of sigma is defined to be, so K of P comma sigma, this is defined to be the inner product Rxy xy divided by norm of x wedge y squared, where xy is any basis of sigma. Okay. And now what you have to check is that this quantity is independent of the choice of basis, right? You have to check this is independent of the choice of basis. So that is because since sigma is a two-dimensional vector space, right? We can pass from any basis of sigma to any other basis of sigma via these elementary operations. One is you interchange the basis elements, xy goes to yx. Another is you multiply one of the basis elements by a scalar, xy goes to lambda x comma y. And the third operation is xy goes to x plus lambda y comma y, right? So we can pass from any basis to the other via these three operations. Is that okay? You believe that? Yes?
Yes.
Okay. That's just something about R2. I mean, two-dimensional vector spaces. All right. And now, when I go from one basis to the other via these operations, it's not hard to see that this quantity is invariant under these operations. Okay. All right.
Yes.
Yes.
I mean, so for example, if I interchange x and y, what happens? This r of xy will be replaced by r of yx, right? Inner product and acting on y, inner product with x. Now r of yx is minus r of xy. So then this will become minus r of xy acting on y and then x. And then the minus r of xy, I can shift to the other side by the skew symmetry. It will become r of xy acting on x inner product with y, right?
Yes.
Okay, so it's invariant under this, and then it's invariant under this operation. That's easy to see, right? If I multiply x by a scalar, then I'll get a lambda squared on top and a lambda squared below. Those will cancel, right? And
Right.
if I add lambda y to x, then what will happen? I'll get r of x plus lambda y, y. So that will be the same as r of xy because r of y comma y is 0, right? Because r is alternating. So
Right.
it will not change, and then I'll get an x plus lambda y here. And so that will give me a term like r of xy lambda y y. So that will be 0 because r of xy is skew symmetric, right? So r of xy y comma y, that will be 0. So this numerator won't change and this denominator is unchanged also under this operation. Okay. So is it clear? This is a simple verification.
Yes.
So I give it to you.
Yes.
I'm not writing this. Okay.
Yes.
That this is invariant. This is independent of the choice of basis. Okay. So this is defined to be the sectional curvature of a two plane. All right. And why is this sectional curvature? Why are these important? Because you can look this up in DOCARMO that knowledge of the sectional curvatures determine the whole curvature operator. Okay. So if you know the sectional curvatures of all two planes, then you know the curvature operator as well. All right. So the curvature operator is determined by these sectional curvatures. Okay. And so this is the standard definition, but I mean, just seeing this doesn't give you any geometric intuition, right? What is this quantity? So one way of seeing this geometrically is this is proved in DOCARMO. You can look at this in the chapter on isometric embeddings. It's proved that the sectional curvature as defined is nothing but the Gaussian curvature of the surface S sigma at P. All right, so this is equal to this quantity R x y x y divided by norm x wedge y squared. Okay, these two are equal. This you can look it up in DOCARMO. Okay. All right. So I think this Gaussian curvature of S sigma, if I remember correctly, DOCARMO mentions this is Riemann's original definition of sectional curvature. I think so. I think so. So it's a very geometric definition, right? It's the Gaussian curvature of a certain surface, right? Tangent, a surface formed by geodesics, right? It's a surface given by geodesics, right? Because it's the image of the exponential,
Right.
image of a plane under the exponential. So, yeah.
Right.
Right, yeah. And I should just mention one more interpretation of the sectional curvature. So if K is equal to, so Kp is equal to, sorry, let me just write. So yeah, so suppose I have sigma is a two-dimensional subspace of TPM. And I take VW is an orthonormal basis of TPM. And I take geodesics, say XT YT. Geodesics, which are tangent to VW at P. All right. So such that, you know, X0 is equal to P is equal to Y0 and DDT T equal to 0, XT equal to V, DDT T equal to 0, YT equal to W. Okay. And then I look at, I follow these for time T. So I have these two geodesics, which make a right angle at P. And I look at XT and this is YT. Okay. And then I look at the distance between XT and YT. Okay. Right. So now, as we saw, the distance function is smooth outside the diagonal, but the square of the distance function is smooth everywhere actually on M cross M. Okay. So let me look at the distance between XT, YT squared, right? So this length is T and this length is T. So if we were in Euclidean space, what would this distance be?
Root 2t.
Right. So the square would be 2t squared, right?
Yes.
So what happens in a general Riemannian manifold is this is 2t squared, and then there is a higher order correction term as t tends to 0, which is minus k sigma over 6 t to the 4, and then there is a big O of t to the 5. Higher order terms, okay, as t tends to 0. Okay, so for a proof of this, there are some notes of Wolfgang Mayer. I can send those to you if you want. The proof is a bit involved. Basically, you have to compute 4 derivatives, actually 5 derivatives of this smooth function. So yeah, so there's quite a bit of calculation, but there are some notes of, I mean, this is not due to Mayer, but he does this in modern language. This formula is due to Cartan, Elie Cartan. So Wolfgang Mayer does this in for a proof in modern language. So if you want, I can send this to you, okay? Or I'll just send you the link because you can just download it yourself. It's a short paper. It's called Topogonov's theorem and its applications, okay? Okay. So what does this mean? So therefore, what it means is that at the first order, the manifold looks Euclidean at the first order, right? This is what you would get from Pythagoras' theorem. But then the curvature enters and controls the higher order behavior of this distance, right? Okay, the sectional curvature controls the higher order. All right, so what it means is, for example, if K sigma is positive, then your picture will look something like this. At higher order, the geodesics are getting a bit closer to each other than in Euclidean space. Okay. Right? Yeah, this is your.
Yes.
Okay. If K sigma is negative, sectional curvature negative, then the picture looks somewhat like this. At higher order, the geodesics are diverging away from each other a bit faster than Euclidean space. Okay. Yes.
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 Okay, so this is, so the sign of sectional curvature, it determines infinitesimally whether geodesics are diverging slower than Euclidean space if the curvature is positive, and faster than Euclidean space if the sectional curvature is negative. Okay, that's what it's measuring. So this is another geometric interpretation of sectional curvature. Okay. So again, Utsav, I just want to say, be careful. This is an infinitesimal property. This is as t tends to 0, as t tends to 0, right?
Yes.
This is not saying anything for large t or even medium t or whatever. This is only for very small t, right?
Yes.
Okay, this is only for very small time, only for very small time. Then, if you want to say anything for large scale time, then you need theorems like the Cartan-Hadamard theorem or Alexandrov's theorem about cat-1 spaces and so on. Those are global theorems which tell you about the behavior of geodesics for all time, right?
Yes.
Okay, so, but those are theorems, they're quite non-trivial, right? Because there what you're doing is you're going from infinitesimal information at every point to global conclusions, right?
Yes.
Okay, so that is not immediate. That's that's highly non-trivial. So those are theorems, right? So, okay. Yeah, so any other questions? Look, just to finish, I won't start talking about Jacobi fields today. We just have 5 minutes. So in these 5 minutes, let me tell you the original, the first definition of Gaussian curvature in the remaining 10 minutes, which is the following. So this is what is taught in introductory courses in differential geometry, where you don't have any mention of the curvature tensor or anything. There you have surfaces embedded in R3. Okay. So let me just explain what is curvature for a surface embedded in R3. Okay. So to give you more geometric feeling for curvature. All right. So we have a surface, say sigma 2, which is embedded in R3 with the induced metric. Okay. All right. Now, so since it's embedded in R3, locally at any point I can get a normal vector field, right? Yeah. So I can get a smooth normal vector field, say N. Okay. So say P is a point in M. And N. So this is a from U subset of, sorry, sigma. P is a point of sigma. So N is defined from a neighborhood of sigma into R3. Smooth unit normal vector field. To sigma. Okay. So this means that the norm of N is constant equal to 1 and N is orthogonal to TQ sigma for all Q in U. Okay. So N at Q is orthogonal. Like this picture. Now what we can do is, if I look at the covariant derivative of N in any direction, right, passing through P. Okay. Yeah. So if I take a vector V in TP sigma, I can look at the derivative of N in the direction of V, right?
Right.
Okay. So then, suppose gamma is a curve passing through P such that, so gamma 0 is P and gamma prime 0 is V. Okay. So now, if I look at, so I know that the norm of N is constant. So if I look at N of gamma T, inner product N of gamma T, this is constant equal to 1, right? So if I differentiate this, then ddt at t equal to 0, this will be equal to 0, right? Yes? Okay. But what is this? This is the, by the Leibniz rule for the inner product, right? This is 2 times inner product nabla Vn with n, right? Yes.
Yes.
Okay. So what does that mean? That means that nabla Vn is perpendicular to n, right? But the orthogonal complement of n is the tangent space, right? Tp sigma. So that means that nabla V of n belongs to Tp sigma. Okay? Right? And so therefore we can get something called the shape operator of the surface, or the Weingarten operator. So the shape operator is the linear map SP from Tp sigma to itself. It's an endomorphism of Tp sigma. Its V goes to nabla Vn. Okay? All right.
Yeah.
Now it turns out that this shape operator is a symmetric operator. So, so this is my SV. So now, so what is inner product SV with W? This is inner product nabla Vn W, right?
Right.
And so what is this going to be? This is going to be ddt at t equal to 0 of with some W of t. Wait, let me think. I've forgotten the proof of this. The
We use
symmetry
the
of
symmetry, right?
yeah,
This will
right.
be minus of covariant derivative of V with respect to n.
Yeah, 1 second. So if I compute this thing, so if let me extend this vector W to a vector field W, capital W, right? So then this is ddt of this minus n nabla VW, right?
Right.
Right?
Right.
And this is 0 because n is perpendicular to W. So this is minus inner product n nabla VW. And let me choose, yeah, right. So this becomes, by symmetry, this is minus n nabla W of some V, right? And then this, by the same argument, this is inner product n, inner product V with nabla W n, right?
Right.
Okay, and so that is inner product V with SW. Okay, so this is a symmetric operator. So it's diagonalizable with respect to an orthonormal basis, right? And so the eigenvectors, these are called. So will you give me just 2 minutes? I'll finish. We've got less than a minute.
Sure,
Just
sure.
give me. I'll finish what I'm saying about this shape operator. Okay. So let me stop and just start another session just for 2 minutes. Okay. Okay. Yeah, so this shape operator is symmetric. Okay. So the eigenvectors E1, E2, the orthonormal basis of eigenvectors, these are called the principal directions at P. Okay. Principal directions. And the eigenvalues, lambda 1, lambda 2, these are called the principal curvatures at P. Okay. Now, the story is the following. You see, if I want to, the point is these principal directions and principal curvatures, these are not intrinsic to the surface. These are not intrinsic in the sense that I cannot measure these using only sigma. That is, using only distances in sigma, I cannot measure the principal directions and the principal curvatures at P. So let me give you an example. So for example, if I take a plane, right? Okay, so then the normal vector is constant, so the shape operator is 0, right? So the everything is 0, right? The principal curvatures are 0. Okay, but this plane, I can isometrically embed this into R3 in a different way as, well, just part of this plane as part of a cylinder, okay? All right, so that distances, let me say, if this is sigma 1 and this is sigma 2, then I have a map from sigma 1 to sigma 2. This is an isometry from sigma 1 to sigma 2. Do you understand? With the intrinsic, okay, right? I can isometrically map a plane to a cylinder. It's not an isometry of the ambient space of R3 to R3. No, it's just an isometry of the surface to the surface. So that means a map which preserves lengths of curves. All right. Yeah, this I can do. Okay. Yeah, now here though, so here the principal curvatures are 0, right? So here lambda 1 is, lambda 2 is 0. But here the principal curvatures, one of the curvatures, if I look at the normal vector, you see the change in the normal vector is like this, along this direction. So when I take inner product of nabla v with v, I'll get +1, right? So one of the principal curvatures is +1. And then in the other direction, if I move upwards, the normal vector doesn't change. So in this direction, nabla vn is 0. So the principal curvatures, lambda 1 is +1 and lambda 2 is 0. Okay, so these principal curvatures are not intrinsic to the surface. That means if I was I mean, this is what people write in most books, that if you are an ant, you know what an ant looks like. If you are an ant in the surface, walking around in the surface, I don't know what this is, what an ant looks like. So an ant will not be able to tell the difference between sigma 1 and sigma 2, right? Okay. The ant can only measure distances in the surface. But I mean, the principal curvatures depend on the embedding of the surface into R3. All right. However, what Gauss discovered was something remarkable, which he called theorema egregium. It means amazing theorem in Latin. That's what he called it, or wonderful theorem. That's what Gauss called his theorem, because he found that so these are the eigenvectors. The product of the principal curvatures, that is an intrinsic quantity. Okay, so the Gaussian curvature is defined to be the determinant of the shape operator. which is lambda 1, lambda 2. And Gauss's Theorema egregium so Gauss was very excited when he discovered this. And it is quite exciting. It says this is intrinsic. This determinant is intrinsic. So it's quite remarkable, right? So you can see here the determinant is 0 into 0 is 0. Here the determinant is 1 into 0, it's still 0, right? Yes?
Yes.
So this determinant is what is defined to be the Gaussian curvature. This is intrinsic. It only depends on the metric on the surface. This only depends on the metric on a surface. So an ant walking around the surface will be able to measure the Gaussian curvature of the surface. The ant will not be able to measure principal curvatures because that depends on how the surface is embedded in R3. But the ant can measure the product of the principal curvatures. That is independent of how the surface is embedded in R3. Okay. And this is the Gaussian curvature. It's the product of the principal curvatures. Okay. So what does positive curvature mean? Positive Gaussian curvature. It means either both the principal curvatures are positive or both negative, right? Yeah. So if you just change the normal vector, you can assume that both the principal curvatures are positive. All right. So there basically, the picture is, so if K is positive, so that means lambda 1, lambda 2 are both positive. So the surface sort of bends the same in both principal directions. So here you see, if I move in this direction, the change in the normal vector, this is the change in the normal vector. This is proportional to the principal direction, right? And also if I move in this principal direction, right, then the change in the normal vector, this is also proportional to the principal direction. Okay, right? My lambda 1, lambda 2 positive. Does this picture make sense?
Yes.
I mean, on the surface of a sphere, look on the surface of a sphere, basically whichever direction I move in fact, all directions are, the shape operator for a sphere is just the identity. So in this case, all directions are eigen directions. So whichever direction I move, the change in the normal vector is proportional to that direction, right? Okay. Yes?
Yes.
Now, if I look at a surface of negative curvature, what happens? So the standard example for this is a saddle, right? So a saddle looks something like this. You have one curve which is going like this, and another curve which is going like this. Okay, and this is your saddle, right? So I've drawn it badly. Sorry, 1 second. Let me fix that. Yeah, so look at this point. If I move, so my principal directions are this direction and this direction. Okay. Now, if I move in this direction, so let me look at this direction here. If I move in this direction, then my normal vector, the change in the normal vector is pointing in the same direction as the change in my base point, right? So this is my lambda 1, this is positive. Okay. But if I move in this direction, in this other principal direction, then what happens to my normal vector? It bends backwards, right? So the change in the normal vector, in this case, is opposite to the change in the base point, right?
Yes.
So my lambda2 here is negative. Okay, so in this case, I'll have lambda1 positive and lambda2 negative. So the product is negative. Okay. All right. So for a surface of negative curvature, at each point, it will look like a saddle locally. It will look like a saddle. I mean, basically, what you can show is that if your surface, it looks like, so sigma locally looks like z equal to f of xy, a surface, a graph over the xy plane. You can choose coordinates like this so that it becomes z equal to the quadratic form lambda1 x squared plus lambda2 y squared. Something like this, okay? You can choose coordinates so that locally it looks like this. So you see that, you know, this will give you a sort of ellipsoid shape if lambda1, lambda2 are both positive, and it will give you a saddle if lambda1 is positive and lambda2 is negative, right? Okay. Is this all right?
Yes.
Yeah, okay. So just to give you some more idea of curvature. So yeah, so Gaussian curvature for a surface in R3, you can describe in terms of the shape operator. So that's quite geometric, right? You're looking at how the normal vector changes and whether the change in the normal vector is in the same direction as the vector or opposite direction as the vector. And in negative curvature, basically, you know, in one principal direction, the change in the normal vector is in the same direction as the vector. And in the other, it's in the opposite direction as the vector. Okay. Does this help to understand at all?
Yes.
Yes.
Okay. Yeah. Okay, so all right, let me stop here then. And thank you for waiting till the extra 15 minutes. Okay, I'll stop here.